Hey dear friends, this is Pradesh Chaudhary Quantum Group. This is the first lecture on electrostatics for JEE Advanced and Olympiad. So before I start electrostatics, let me tell you a few things about how I am going to proceed these lectures for this playlist, and also a few points in general about electrostatics. So number one is that obviously this is especially for JEE Advanced and Olympiad. So here I will, in these lectures, I'll give relevant theory relevant especially for JEE Advanced and Olympiads, and that will be supported with examples specially meant for JEE Advanced and Olympiad. So there will be a lot of integration involved, calculus would be involved, hence electrostatics also sometimes calls a mini calculus course. So maths will be there, that is one thing. So that might not be suitable for those preparing for NEET, because in NEET simple questions come, direct formula based questions come. So that is one thing. And about electrostatics in general, it is a vast chapter. It is the foundation of the electrodynamics. So it is a long chapter, so we'll do quite in detail. And sometime few students might think that whatever I'm teaching, that is actually not necessary. But because this is aimed especially for JEE Advanced and especially for those who aim for the greater ranks, so there will be a lot of things that is not usually taught in the classroom teaching. So I'll cover all those things, and that will be supported with a lot of examples. So with that note, let me start this chapter. Very good chapter, electrostatics. So what is electrostatics? So in electrostatics, the word electrostatics comes from two things: electro and static. Electro means something related to charge, and static is obviously at rest. So in electrostatic, we study the effects of a static charge. So it is a branch of physics that deals with the electric effects of static charge, right? So now the question comes, what is a charge? What is charge? From where the charge comes? So charge, we can say that the charge is the fundamental property of matter. In fact, there are two fundamental properties of matter. One is the mass that we know that the something has a mass 2 kg, 3 kg. There's different thing, matter and mass. Matter is the something that has some volume, and that matter has a specific property, mass. So by virtue of that property, mass, there is the gravitational force between matter. And similarly, there is another property of matter, that is charge. So by virtue of charge, the material that has a charge, they can have forces like attraction, repulsion, and when charge moves, it creates something called magnetic field, and in that magnetic field, if another moving charge is there, that explains the force. So that is the charge. So we can say that charge is the fundamental property of matter that is responsible for electromagnetic effects. So charge of a material body or particle is a property due to which it produces and experiences electrical and magnetic effects. So now, from where do charge come from? So obviously charge comes from matter. Without matter, charge cannot be there. So when we talk about the matter, the fundamental unit of a matter is an atom. So in an atom, there is a nucleus, and surrounding nucleus there are electrons revolving. So in nucleus, there are protons and neutrons. Neutrons have no charge. Proton has a, we say that, a positive charge, and electrons have negative charge. So that is the fundamental origin of the charges. It come from the matter. So charges are everywhere. Where there is matter, there are electron, proton. So there are charges. And now property of charge. The first property of charge, there are two states of charge. Charge comes in two states, positive charge and negative charge. So positive charge or the negative charge, like the like charges repel, and unlike charges attract. So that is very clear thing, so need not to be elaborated. So this is the important thing, quantization of charge. What do you mean by the word quantization? When we say quantization, mean something which is quantized, it comes in certain packets. Like suppose we use currency notes. Suppose demonetization against comes, and Narendra Modi demonetizes all goods except the rupees 500. So whatever we can buy or purchase, the amount has to be in multiple of 500. So that is meaning of the quantization. So like once again we can think like, suppose a photon has a energy in multiple of h nu. So the minimum energy is h nu. So in the packets of h nu we can have energy. If a string is fixed at both ends, and the frequency of any possible modes can be multiple of v by 12. So that is a quantization. Same way, charge is quantized mean it will occur in nature in a multiple of certain number, that is called the fundamental charge E. So charge of a particle or a body is always integral multiple of a fundamental charge, that is a E. So the value of E is 1.6 into 10 to the power minus 19 coulomb. Unit of charge is a coulomb. So we can have a charge in a multiple of E, and as any integer can be positive or negative. So the possible charges can be plus minus E, plus minus 2E, plus minus 3E, plus minus 100E, like that. And we cannot have a charges like minus 1.2e or minus 3.7e or plus 4.8e, something like that. We cannot have any charge that is not an integral multiple of e. So like this. So this is the meaning of quantization of charge. Now, conservation of charge. That is also one of the fundamental conservation law in nature. So suppose we have an isolated system. What do you mean by isolated system? A system which does not interact with the other. So like, first let me explain. So it means an isolated system. For an isolated system, total charge is conserved. Suppose this is a conducting sphere, that is also another conducting sphere, and they are connected by can be connected by a conducting wire. Right now there is an open switch, and suppose initially at this moment there are charges, say this A has a charge say QA and B has a charge QB. They have a charge themselves. They can be placed in air or somewhere. Even suppose, just you think one thing, like suppose there is some wire, some electric current is going on a wire. Even there is no covering, that is a naked wire, still if I'm at a certain distance I am safe, because between that wire and me there is a air, that is a dielectric. The charge of the wire cannot come to me through the air, so that cannot come to me. But sometime in some circumstances the charge of the wire can come to me through the air if there is a dielectric withdrawal, something like that. So here that is mean of isolated. The charge of A and B is only between them and nothing else. So that will be conserved. It cannot be destroyed, cannot be created. So what we can do now, if I close this switch, so kind of an electrical contact is made between A and B, so that switch close slip facilitates the flow of charge. Due to flow of charge, due to some mechanism, now the new charge between on A become QA dash and on B become QB dash. So that can change, but the total charge cannot decrease, cannot increase, it will remain conserved. That is the meaning of conservation of charge. So final charge, the final total charge QA dash plus QB dash is equal to initial total charge QA plus QB, and that is what we mean by conservation of charge. Okay. Then the next properties, and these are, I can say, miscellaneous properties. So what are the miscellaneous properties? Charge is obviously scalar quantity. SI unit is a coulomb. The charge is always associated with mass or matter. We cannot have charge without matter. To have a body charge, it must be in a matter, obviously, because obviously the charge is the fundamental origin of the charge is the matter from the atom. So charge can't exist without mass, though mass can exist with without charge. That should be here. The mass can exist without charge. Here I should return that without charge. Second thing. Third, charge is relativistically invariant. So what do that mean? Invariant mean that does not change. Relativistically mean the velocity, obviously. I mean, if suppose there is some charge that is at rest, and now suppose the that start moving, so charge doesn't change. Mass changes from the special theory of relativity. Length changes, time interval changes. So that you will study when you will study special theory of relativity. I am not going to go into that. So basically, think of there is matter has some charge and that is at rest, and that will not change if it moves. So charge is relativistically invariant. That is what the mean. And next, a charge at rest produces electric field, and a charge in motion produces a magnetic field. So charge at rest produces one electric field around itself. A charge with a moving with a uniform velocity produces electric field and magnetic field both. And an accelerating charge emits electromagnetic radiation. So these are few basic properties of charge. Okay. Now there are three types of material. So let's see this picture first. So see, you can see that. So this is a matter, and this is a fundamental unit of a matter, that is an atom. So this is a nucleus. Electrons are revolving around the nucleus. This is a last orbit, is the valence orbit. So what happens? The electron of the valence orbit is far away from the nucleus, so it is the attraction of that electron from the nucleus is weak. So if it can get some energy from the room temperature by some other means, so that can leave the nucleus. So from where it can go? So the atom of a valence shell, the electron of the valence shell may leave the parent atom if it gets a sufficient energy, and after leaving, where it will go? So in matter there are a lot of atoms and there is a lot of space between the atoms. So the electrons that leaves its parent atom but still hasn't left the whole matter. So it moves within the interior, within the empty spaces between the atoms within the matter, and such electron is called a free electron. And just if you can recall the atomic theory, the average speed of the electron revolving around the nucleus is of the order of 10 to the power 5, 10 to the power 6 meter per second. A lot of free electrons of the order of the Avogadro's number. And when they leave the valence orbit, its speed is not going to become to rest. That will still be moving around that speed. So there can be a lot of free electrons moving with a great speed. So that can move within the interior of the matter. So now there can be three types of material based on this. The one material is that which have a lot of free electrons. So there are a lot of free electrons, so there will be a lot of conduction. Such a material is called a conductor. So there are a lot of free electrons. If I just visualize that thing in conductor, so those free electrons are moving with a lot of speed of the order of 10 to the power 5, 10 to the power 6 meter per second, and they are plenty in number. So of the order of Avogadro's number. So within a very small volume, there are so large number of free electrons moving with such a large speed. So it can be best viewed as a kind of a gas, like ideal gas. So the motion will be very random in a confined volume. So we can think the free electron inside a conductor as an electron gas. So just imagine there is an electron, negatively charged electron cloud, and nearby that some positive charge will come. So they will just as a whole attract towards that, and if a negative charge is there, that will repel, so they will move away. So the flow of charge can be allowed within the conductor, and it is responsible for the electrical conduction. Such a material which have a large number of electrons are the conductor. And then there is an insulator. They have very less number of free electrons. And between insulator and conductor, there is another category that is called the semiconductor. So the free electron density in the semiconductor is the intermediate between the conductor and the insulator. The order of the electron density in a conductor is of the order of 10 to the power 28 per meter cube, 10 to the power 29 per meter cube. So that is a huge number. So these are three types of material. So in this chapter, we will be concerned with basically two materials, conductors and non-conductors for the insulator. So we'll start basically with the non-conducting materials, and in the latter part of this chapter, we'll talk about the conductor, and they have very special properties, so they will be dealt separately. So now we'll talk about the charge density. Like we know what is the mass density, we know about the energy density. Normally in the lower classes, when you say about density, you just say the mass upon volume. So actually only at that level you study only that density. So we can have so many density like mass density we already had, we can have a charge density, we can have energy density. So suppose if I say X density, for some physical thing to have a density, that need to be confined, that should be confined within a volume. So mass can obviously be confined in a volume, charge can be obviously be confined in a volume, energy can be confined in a volume, so we can have their energy. So now coming to the charge density, that is basically charge per unit volume or the charge contained in the unit volume. So the first density is we call the volume charge density, that is the main density. Obviously the charge can be confined in a volume. So volume charge density is charge confined per unit volume. So let me elaborate a bit more. Suppose this is some charge body, and this is a point P, and with a coordinate system, with respect to coordinate system, the position vector of this point P is say R. So density is actually a point function, meaning a different density can be assigned to different points. So here it is a point function, and I want to define a charge density at this point. So basically the idea is charge per unit volume. So to have a charge, it should have some volume. But if I take a greater volume, so the point will be changed. I mean, it will, suppose if I talk about this point specifically, and the volume I am giving you is this much volume. So in this much volume, there are so many points. So I wanted to define the charge density at this point, but now there are a lot of points there. So the trick is that we can define charge density at here, and the charge is also within a volume. So what I will take a very small volume surrounding that point. So still that is a very infinitesimal volume. So specifically now I can say that the charge density is at this point. So we want to define charge density at point P. So suppose in the neighborhood of that point P, a very small infinitesimal volume dV is there. In that volume, if there is a charge dq, so we say that the volume charge density at the point P is charge contained around that infinitesimal volume around that point, that is a dq by dv. So that is the definition of a volume charge density. Now some few simplifications that we define. So if we want to define the total charge of matter, I took this small volume. In this volume there was a charge dq, so rho is a dq by dv, and before that, so rho is a dq by dv. So arrange this thing, I can write dq is equal to rho dv, and if I integrate this equation both sides and integrate in such a way that this integration covers all the points of that body, so this integration will become, this is a q total is equal to integration of rho dv, and that integration has to be carried through the whole body. And if this rho is constant. From this integration, if the rho is constant, that will go outside the integration, and that will go outside, and integration of dV will become the V total in total volume. So I can write rho is equal to Q total by V total, mean total charge upon total volume, and that is when the charge density is uniform. If the charge density is not uniform, we'll see how the charge varies and we'll then integrate. So for that we have this example. Suppose in this example what is given, that this is first of all, this is a sphere. This sphere radius. Charge density varies with the smaller. For the smaller the distance of a point from the center. The variation is charge density is rho is equal to A r power n. A is constant, n is also constant. Obviously, n is not something like less than 1, and the n is not negative, otherwise that will be some rho is equal to A upon r power something, and at r is equal to 0, there will be, that will shoot up. So what we have to find, we have to find the total charge content within the sphere. This example is a very standard example, and I'll use this result later when we'll talk about the electric field. So this is a very standard result, and whatever result that we'll obtain, we'll be using. Now let's go to next page. So given was that a sphere, and the charge density was rho is equal to A r power n. Its radius is capital R here. So element that I want to take here in a sphere, how I can construct the sphere with a small element. The small element that I can take is a shell. This is a shell having between the radius r to r plus dr. So this is a shell of thickness dr, but dr is very small. This is a very thin shell. So if I increase this r from, I will take this r from 0 to capital R. So through this shell I can construct that whole sphere. Now what is the volume of the shell? So that is a direct thing, like still if I want to write the volume up to radius r, the volume up to radius r is a V. So that V is equal to 4 pi r cube by 3. And if I increase radius from r to dr, so there is an incremental change in the volume. That incremental change in volume is dV. So from here, if I differentiate, I will get dV by dr is equal to, that will be pi 3, 4 pi r square. So this volume dV is actually the 4 pi r square dr. And now the charge contained on this ring, say dq. We know that rho is equal to dq by dv, so dq is equal to rho dv. And put the value of rho here and dv here. So putting this, we will get 4 pi. This I'm putting direct 4 pi a. There is a r square. This is r power n, so that will be r power n plus 2, and that is dr. Now integrated to get the total charge. So Q total is integration of dq, and if I integrate it, I'll take constant outside. So 4 pi a r power n plus 2 dr. We'll take this variable r from 0 to capital R to cover the whole of the sphere. So finally we'll get that Q total is equal to 4 pi a. That will be, if I integrate it, this will become r power n plus 3 by n plus 3, and putting the limit, we'll get capital R power n plus 3 divided by n plus 3. That is this equation. And now there is another kind of charge density, that is the surface charge density, sigma. When we'll use surface charge density, the material has to be a planar body, a lamina which has a uniform thickness, something like this. It is used for a sheet lamina of uniform thickness. So So like this, suppose this is a lamina of thickness say T everywhere, and if I just insert a pill box on an area say dA, this is the area dA, here I insert a pill box. So within that part, this part, the total charge, this is a non-conductor obviously, so charge is within that whole volume. So on this whole volume, the thickness is T, area is A, the volume is a T into dA. So in this whole volume, the charge is say dq. So we will define surface charge density as a charge spread over unit for area. So here the surface charge density sigma is dq by dA, dq by dA. And this dq can also be written in terms of the volume charge density. Suppose its volume charge density is rho. So we had earlier written the charge, rho is equal to dq by dv. So dq is equal to rho into dv. So that is a rho, and this volume is T into dA and divided by dA. So that dA will get cancelled. So we can also have a relationship between corresponding volume charge density and the surface charge density with the thickness of the sheet, and that is sigma is equal to rho T. So now if again sigma is a constant, so writing this, I want to write the total charge, so I can write this dq is equal to sigma dA, and to get total charge, q is integration of dq, and integration of dq is sigma dA. If sigma is a constant, sigma will come outside, integration of dA will become total charge. So we will have total charge is equal to sigma into total area. So sigma is equal to total charge upon total area. So, and that is when the sigma is constant. Now we can take one example for the charge and surface charge density also. So here, this is a disk, non-conducting disk, radius r. The charge density at a distance small r from the center varies like this: sigma naught 1 minus small r square by capital R square. So we have to find the total charge in this disk. Let's go ahead. So once again we'll take element, and now it is a 2D diagram. Object is also 2D. Earlier that was a sphere. So the element would be a ring. In the last case that was a shell. The element is a ring of radius r and thickness dr, and the area up to radius r is a. So a is equal to pi r square. So when I increase radius from r to r plus dr, the incremental change in the area is dA. So I can write from here dA by dr is a 2 pi r. So dA would be 2 pi r dr. There is another way to get that. Suppose you just cut that ring, and after cutting straighten the ring. So that ring would be of the length 2 pi r and thickness would be dr. So area would be 2 pi r into dr. And now the charge on this ring, this elemental ring, suppose the charge here is on dq. So sigma is equal to dq by dA. So dq is equal to sigma into dA. And sigma was given to be sigma naught 1 minus small r square by capital R square. So putting that thing, we can write sigma naught 1 minus r square by capital R square, and dA is 2 pi r dr. So q total is integration of dq. So for the integration I can take 2 pi sigma naught outside, and within integram there will be r into an r minus r into r square r cube by capital R square dr. And if I take this ring from radius small r is equal to 0 to capital R, through that ring will cover the whole disk. So the limit would be 0 to capital R. Integrating this, we'll get Q total is equal to 2 pi sigma naught. The first integration will be R square by 2. And this integration will be capital R power 4 by capital R square. So that will be capital R square by 4. So simplifying that thing, we'll get this is a sigma naught into pi R square by 2. So there is a one way also to look at this thing. What is one way? If the surface charge density was sigma naught, so total charge would be sigma naught into pi R square. Now the surface charge density is sigma naught into 1 minus small r square by capital square. So total charge is this. So we can think that this disk has an average surface charge density sigma naught, so that for the area pi r square, the total charge has become sigma naught by 2 pi r square. Alright. Now another density, that is the linear charge density. So we use linear charge density for a body whose cross-sectional area is same everywhere. Doesn't matter whether that cross-section is circular, a square, or of any shape. So like suppose this is a wire and this is a cross-section. So every year it has the same cross-section. Suppose this cross-section has an area A. And like we have defined a volume charge density as a charge per unit volume, surface charge density is a charge per unit area. The same way linear charge density is a charge contained per unit length. So I take a small length, say this length is a dl, and in this length total charge contained is dq. So at this location, it can be at different locations. So at this location, the linear charge density is the charge contained dq per unit length dl. So dq by dl. And we can write in terms of that rho also. So here the dq in terms of rho, dq is a rho into volume. So the rho, the volume charge density, the volume of the shown part is the A into dl and then divide by dl. So this lambda in terms of rho can be written as a rho A. Sigma in terms of rho was the rho T, lambda in terms of rho is rho A. And once again, if lambda is constant same way that I had written for the volume charge density, surface charge density, then we can write the lambda is equal to total charge upon total length, like that. Okay, and we can take one example on the linear charge density also. So here this is an example. This is a ring of non-conducting charge ring of radius r, and this is a reference line x-axis from where I can have an angular position. So at the angular position theta from this reference line, the linear charge density varies with theta as a lambda naught sine square theta. Lambda naught is a constant, theta is the angular position. So we have to find the total charge of the ring. So we can have some idea, like if this was not sine square theta, only sine theta, so on half the part charge would be positive, on half the part charge would be negative, so total charge would be 0. So here, because it is a positive, sine theta first increases. Here the lambda is maximum, then lambda is 0, then increases, the lambda is maximum here, and positive, then lambda decreases, and here in negative lambda increases and then decreases. So overall charge would be 0. But the sine square ensures that there is some total positive charge. So that's what we have to find. So go to next page. So here that was the ring. We have to take an element. So for the element, I will take some element between angular position theta to theta plus d theta. So that is my element. This element has a length. If the radius is r, so this length is r d theta, and obviously then this element would be having charge dq is equal to a local charge density there lambda into that length is r d theta. So this dq I can write lambda r d theta, and lambda was lambda naught sine square theta r, yeah, r d theta. So now it's just a matter of integration. So if I want to find the q total, so I will have to integrate this dq, and that is a lambda naught outside and integration of sine square theta d theta from where 0 to 2 pi. And see, this is very standard integral. It is used a lot of times, so you should remember this direct result. And also you should remember that what is the average value of sine square theta from 0 to pi by 2, that is half. So for that integration, I can write this sine square theta can be written as a 1 minus cos 2 theta by 2, like that. So the integration of sine square theta with respect to theta mean the integration of 1 minus cos 2 theta with respect to theta. And this integration 1 by 2 will go outside, and integration of 1 is theta, and integration of cos 2 theta is a sine 2 theta by 2. And if I want to make this integration from 0 to pi by 2 here, so 0 to pi by 2, and that 0 to pi by 2, if I put the limit for the theta, that will be pi by 2, and for the sine 2 theta, when this theta is pi by 2, means sine 2 pi by 2 is pi 0, and 0 sine 0 0. So that is a very important integral for physics. It comes so many times, so just remember directly. Next time if it will come, I'll use directly. That is a pi by 4. So 0 to pi by 2, the answer is pi by 4. So for 0 to 2 pi, that will be 4 times of that. So that will be just pi. So this is lambda naught pi r. So what I can also write this lambda naught by 2 into 2 pi r. Why I am writing this? See, if it was having a uniform linear charge density lambda naught, total length is 2 pi, then the total charge would be lambda naught in 2 pi r. Now the charge density is lambda naught, sorry, lambda is equal to lambda naught sine square theta. So total charge has come a lambda naught by 2 into 2 pi r. So what does it mean? That you can think like that now the average linear charge density has become lambda naught by 2, and that is because of this sine square theta. The average value of sine square theta from 0 to pi by 2, and in any multiple of 0 to pi by 2 is 1 by 2. So this sine square theta is making the average value of lambda to be a half, to be lambda naught by 2. So that's why it is the total charge is lambda naught by 2 into total length 2 pi r. So now I can mix the two questions, linear charge density and the surface charge density. So earlier in the disk there was a variation with r, and the ring there was variation with theta. So now I mix both things. So here in this question, there's a non-conducting disk of radius r. The surface charge density depends on both r as well as the angular position theta, as sigma naught 1 minus small r square by capital square into sine square theta. So it is varying with r as well as theta. So at a particular r, as I go from here to here, so that part would be constant, theta part will. So if I go from here to here, so then this part would be constant, that part would be varying. So we have to find the total charge contained within the disk. So for this thing there is a special technique called double integral, but that I will not use because most of it is not taught at 10 plus 2 level. So I will take a two-step method. So how I'll proceed? So that is my disk, and this is a ring. from, I'm not showing it, but I've taken few examples so you can clearly understand. So this is between r to r plus dr, and this angular position I can that write, this is theta and this is d theta. So just see this element, this is an element. So this element is between radius r to r plus dr and angular width theta to theta plus d theta. So see, this length is r d theta and this length is dr. So see carefully, this radius is r and this is d theta. So this is r d theta and this is dr. So that area, the shown element has an area dA is equal to r d theta into dr. And suppose this element has a charge, say del q. So del q is obviously, this del q is the local charge density at this element, that is a sigma into dA. So sigma is equal to sigma naught 1 minus r square by capital R square into sine square theta, and d is this, d I can write this r dr into d theta, r dr into d theta. Now if I take this element on this elemental ring, if I go on this elemental ring, the radius is between r to r plus dr. So r does not change. So dr is so small. That is the beauty of the calculus. So on this, if I take this element from here to here, only theta varies. So on this part, this sigma naught is fixed. 1 minus small s square by capital R square is fixed. R dr is fixed. The only variation is with theta. So this part charge is a del q and this whole charge is say dq. So charge of this ring is say dq. Charge of this ring is say dq. And this dq is the integration of del q. So dq is integration of del q, and on this integration all the constant thing, all the things which are in terms of smaller, that are constant. So I'll take outside the integration. So sigma naught 1 minus r square by capital R square and r dr, and within the integration, that is a sine square theta and d theta, and that theta has to be taken from 0 to 2 pi, and we had just calculated this integral that had come to be a pi. So this will be sigma naught into pi, and that is a, let me simplify that thing, r minus r cube by capital R square dr. Now we can go to the next page. Let me check everything is right. This is pi sigma naught and that will be right. So now what I want to do, if I just make so many rings like this, all such rings, if I let the radius vary from 0 to capital R through these rings, the whole disk will be covered. So here if I integrate all such dq's and vary radius small r from 0 to capital R, that will give me the total charge. So total charge q total is the integration of that thing, and that is the integration of this thing, and this is 0 to capital R. And just before we did the same integration, that had come to be r square by 4. So I'll write that. So that will be q total is equal to sigma naught pi r square by 4. So that is a sigma naught by 2 pi r square, sigma naught by 4. And let's see the meaning of that thing. See here, see 1 minute. In this question, the sigma was sigma naught 1 minus r square by capital R square. The total charge was just sigma naught by 2 pi r square. And understandably, here the answer is sigma naught by 4 pi r square, and that is because here another term, this in sigma, another term sine square theta also come, that makes the average further reduced by a factor of half, because the average of sine square theta in the multiple of 0 to 2 pi is 1 by 2. So that is the answer for this thing. So thank you for watching this video. Stay tuned, there will be great things coming for the next videos, next lectures. Thank you. Enjoy physics.